about the second most famous number in maths, the second most important number in maths, and also logarithms. So I guess logarithms should also be in the title. We'll put logarithms in there. Logarithms. Let's draw a line underneath it. So now we know we're doing both of these things. Okay, so we know pi, right? The Greek letter pi. That's approximately equal to 3.141592658, whatever. We know that. Now Euler was a German and Swiss mathematician in like 1700s, and the number is named after him. Many things are named after him actually, but this number is given by the letter E, and this is approximately equal to, well, we don't know. We're gonna find out ourselves. So how do we do it? Well, it actually comes from compound interest. So let's say the formula for compound interest says that the final value that we have is equal to the initial value. So I'm going to write IV for initial value times 1 plus the interest rate, that would be R over 100, to the power of time. So however many times you do it, right? So IV is initial value, R is interest rate, and then T is time. So let's say I gave you $1 to start with. We're always starting with $1 in this case. So you have $1. And then I tell you I'll give you 100% interest, but only once a year. So I'm telling you 1 plus 100%. So that would be 100 divided by 100. So that's just 1. But I'm only giving it to you once a year. So that's to the power 1. That is equal to 2 to the power 1, which is equal to 2. Okay, so you would have $2 by the end of 1 year. Let's show that 2 better. Now, if I told you that I'm going to give you that interest twice a year, but I'm only going to give you 50% because, balance it out, then what would you have? You would have 1, and then you would have 1 plus 50 over 100 to the power of 2, because you're doing it 2 times per year. And that is approximately 1.5 squared. That is equal to 2.25. So now you would have $2.25. Okay, so far, the more times you have it, the better it is for you. Let's try if I gave it to you 4 times a year. But of course, I'd only give you 25%. So we would have, I'm just going to stop writing the 1 over there because that doesn't make a difference. So you would have 1 plus 25 over 100 to the power of 4. Because I'm giving it to you 4 times a year. And that is approximately equal to 2.44. So clearly, once we only had given to us once a year, we had just $2, and then we had a 25-cent increase, and then we had a 19-cent increase when we did it 4 times a year. Let's say I give it to you every month, and then of course that would be 12 times a year. So you would have 1 plus, and now every month, so the interest rate would be just 100 divided by how many months there are. So that's 12. So that's the numerator, and then that is divided by a whole 100 right here to the power of 12. And that is approximately equal to 2.613. Okay, so we're getting closer and closer to some number. Does this number go to 3? Does it go to 2.8? What does it go to? Well, so let's write it in a general form. So generally, what we're doing is we're doing 1 plus 100 divided by n. N is like the interest rate. All of that divided by 100 to the power of n. You can see it was exactly what we've been doing. We're doing 100 divided by 12 divided by 100 to the power 12. This is 100 divided by 4, which is 25, divided by 100 to the power of 4. Same thing over here, same thing over here. So now let's simplify this right here. So 100 divided by n divided by 100. So if you divide this whole thing by 100, that's like multiplying by 100 over 1, multiplying by 1 over 100. So that's times 1 over 100. So what do we get? Well, the hundreds cancel out. You're left with 1 over n. So what we actually have is 1 plus 1 over n to the power of n. Now the whole idea is, what if I kept on giving you an infinitely small amount of interest? So this is the interest rate right here, right? If I gave you a very small number, but then I gave it to you so many times, because that's what we've been doing. We're getting smaller and smaller numbers here, but we're doing it so many times. And clearly that's increasing a value, right? So mathematically, or formally, you will write this as the limit as n approaches infinity. Infinity just means I'm doing it so many times. N approaches infinity of 1 plus 1 over n to the power of n. And that is equal to E. That is the definition of E. And that is this is also like pi, it's repeating forever. This is approximately equal to 2.613. 71828, and then so on and so forth. So that's the value we're approaching, and that's the value of E. So now we will see why this is actually useful. Okay, compound interest, pretty interesting, but what's so useful about this? And now we need to learn about logarithms. So let's do this right here. Logs. Well, if I told you to solve 2 to the power x is equal to 32, well, you can just guess, right? You know, 2 to the power 1 is 2, power 2 is 4, power 3 is 8, power 4 is 16, power 5 is 32. So you would say x is equal to 5. Okay. If I told you 2 to the power x is equal to 64, what would you say? Well, that's pretty simple. X is equal to 6. But as soon as I tell you to solve 2 to the power x is equal to, let's say, 56, what is x equal to? Well, we don't know, because, well, clearly it's between 5 and 6, because it's going to end up between 32 and 64. So we'd assume it's like 5.4 maybe. Who knows, right? We don't know what it is. And this is where logs come in. So logs help us solve these type of equations. And now we need some notation as well. So in this example right here, 2 is called the base. X is called the index. And 56, or we can just call it like our result. Let's call it our result, right? So what we're going to do is, logs are basically the inverse of powers. So we know 2 to the power x equals 56. Now how do we find x? Well, what do we do? So we do log base 2 of 56 is equal to x. So this is how you write it. So the log of base something, so this is like a underscript, it's called subscript, yeah, subscript, of the result gives you the index. So this is now useful in helping us find the index. Before we're working with indices, now we're working with the result and we're trying to get the actual index that we used. So let's go to this side right here. Let's go to the left side. So we have different types of bases. We can have log base 5 of 56 is equal to x. What does that mean? That means 5 to the x is equal to 56. We take this to the power x is equal to 56. If I told you log base 21 of 99 is equal to k, what does that mean? That means that 21 to the power of k is equal to 99. Right now we're not learning how to solve these equations. Right now we're just learning what this logs means. And the most common log, or I guess one of the most common logs, is just log base 10. And it's so common that we don't even write 10. So once you just see log, and let's say I gave you 100, right? What's that equal to? Well, if you don't have a base given to you, you can assume that is equal to base 10. So this is the same as log base 10. And that is equal to x. But we know what this is. We can solve this one. We can say x is equal to 2. Because we know 10 squared is equal to 100. Now, back to e. So we come here. So we have log base, let's say, 15 of 35 is equal to x. I'm just going to write this again so you guys remember what I'm talking about. So that means 15 to the power x is equal to 35. And if I just had log written by itself, let's say I had 500 is equal to k, that means 10 to the power k is equal to 500. So this is what we have. And then from here we went to this to solve the equation, but we don't know how to solve it just yet. Actually, the log button is on your calculator, but we won't worry about that right now. Now, the important thing is e. So e is just a number, right? So 10 is a number, 15 is a number. These are just numbers. Now the log base e of, let's say, whatever we want. Let's say we have 5, right? Is equal to, let's say, y. That means e to the power y is equal to 5. Now this is so common, log base e is so common that we call this the natural log. This is called the natural logarithm. And it has a special way of writing it. So we don't write, no one writes log base e. It's either log like this, which means log base 10, or we have log base e, which is actually written as ln. So that is L and that is an n. And ln just means log base e. So if I said ln 5, that actually means e to the power, let's say, k is equal to 5. That's log e of 5 is the same as ln of 5. Now, what's so natural about this logarithm? Well, we don't know yet, and we're going to learn in the next video on how to actually solve these type of equations, what the values for these would be. But E is so special because of so many applications that it has. So if you like just do some reading online, if you search up econometrics, it has applications in econometrics when you're doing linear regression, for example. This is like high level economics and conducting analysis on different types of data, linear regression. Even in maths, when you do differentiation and integration, then E has some very special properties. And actually, you can have a whole video just on E, to be honest. But this is so special because let's say you had the function y is equal to e to the power x, right? This is just a number to the power x. The derivative of that function is actually equal to the function itself, which means that the integral of that function is also equal to the function by itself. And this function and 0 are the only two functions where the derivative and their integral and the function itself are equal to themselves. So yeah, that's E for you right there. So E is very, very useful, very, very common. And next video we will see how to use logarithms. We'll look at natural logarithms and we'll look at some rules on how they work. So yeah, I hope you enjoyed the video. If you did, please like, share, comment, subscribe, and let me know what else you want to see in future videos.